Yes, hello everyone, and I just want to welcome everyone to the fall CDY Seminar series. I think several of you were at the Gamma Ray Binaries workshop in Dalkey a few weeks ago, and that was a highly successful workshop that we had. And now we are continuing our seminar series on the topic of microquasars. And as you know, it has generated a lot of interest lately. So for this series, we now have a set of 4 talks on high energy studies of microquasars, and I hope that you can continue to join every other Wednesday. And to kick it off today, we have Laura Olivera-Nieto, who will give a talk on the topic microquasars, the nearest black hole particle accelerators. So just a quick introduction. Laura is an expert on the topic. Her PhD thesis was on this subject, and she received her PhD in astrophysics from MPIK Heidelberg, working with Jim Hinton and Brian Reville. And she did her master's at the University of Innsbruck. I just want to mention that she was awarded the highly prestigious Heidelberg Willem and Elsa Heras Dissertation Prize for Physics and Astronomy in 2023, which is a real honor. And in addition, she also received the 2024 Otto Hahn Award, Max-Planck Society Thesis Award, and also the 2024 Otto Hahn Medal. So congratulations for that, and we are very happy that you could start us off with these seminar series. So Laura is currently a postdoctoral researcher at MPIK. So please welcome me in joining Laura. And just to remind you, the format of our talk, we usually do about 50 minutes, and then we have questions related to the topic. And then we keep the floor open for just any general discussions, even broadly connected. And if you are not receiving our emails directly, then please put your email in the chat, and we will sign you up so that you can receive the direct emails. So thank you for coming, and Laura, please get started. You are already sharing your screen. Great, thank you.
Right, so what I was saying is that I'm going to give the first talk of actually 4 on recent results on microquasars. And so this talk is going to be heavily biased towards the results of the HESS Observatory, because that's where I am a part of a collaboration of, and also where most of my work has been carried out. But that being said, I'm going to try to sort of give a bit of a bigger picture, because it's the first talk, and sort of try to motivate a bit like why all of this sudden interest about microquasars. Because this audience might be a bit mixed, so some people are, really experts on the topic. Some people might be listening to it for the first time. I also am going to try to give it a little bit of an introduction, hopefully deep enough and fast enough at the same time. So, the question that animates the field of astroparticle physics, right, is of course the cosmic ray flux, right? So the Earth is hit continuously by a flux of charged cosmic ray particles. And of course, we want to answer the question, where do they come from and how are they accelerated? And this is a nice picture that I got on the internet. Of course, this is not a scientific plot. This is the scientific plot somehow of cosmic ray research, which is the cosmic ray spectrum. So on the y-axis, you have essentially the flux of cosmic rays. So how many do we get per second, per steradian, and per meter square? And on the x-axis, you have the energy. And so the remarkable thing about this plot is that it really spans very many orders of magnitude, both in flux and also in energy. So we know these particles are accelerated somewhere, and now the sort of research question becomes like, how and where are they accelerated? So the picture that we have, you have some sort of mysterious source, which is accelerating protons and also electrons. And the ideal thing for us would be to just be able to see these particles. But because these particles are charged, they actually don't travel in a straight line to us. So they do these sort of crazy trajectories, meaning that, our little telescope that I put at this side cannot really see them directly. So when we detect them on Earth, they don't really remember where they came from, essentially. Luckily for us, however, the universe is filled with both light, in this case, these blue balls are low energy photons, and also gas. And the particles interact with this. So both the electrons would interact with the photons and the protons would interact with the gas. This is, I'm thinking of galactic sources, so photopion production is not so important. And then make high energy photons. And these high energy photons is what we detect. So we don't detect the particles directly, we trace them by the presence of gamma rays. So I put here the 2 sort of sketches for the processes that I mentioned that are sort of most relevant for this talk. If you have accelerated electrons or high energy electrons, they will interact with ambient low energy photons through inverse quantum scattering and essentially bump a photon up and make it into a high energy photon. And on the other hand, protons will interact with dense ambient sort of nearby gas, make a pion, which then decays into 2 high energy photons. And so Again, we don't trace the particles themselves, we trace sort of their imprint in the surrounding media somehow. Now here I put a little picture of the HESS, something that looks like a HESS telescope. A way that we detect these gamma rays is imaging atmospheric Cherenkov telescopes, we call them IACTs, which are, for all purposes, what you picture us as a telescope. So it has to work at night, and we have to point it at whatever we want to see. However, that's not the only type of gamma ray instrument. There's also something like this, and this is a picture of HAWK, which is actually 300 water tanks somewhere up in the mountain in Mexico. And HAWK detects gamma rays not sort of through in the night sky, but inside of these water tanks. And because of that, it doesn't have to be pointed anywhere, and it can observe sort of day and night. And so, of course, this comes at a cost, and the cost is that the angular resolution and the energy resolution of an instrument like this is worse than an instrument like HESS. So you have this sort of two classes, HAWK, LASSO, which are perfect for detecting, sort of seeing everything all at once. And then you have something like HESS or MAGIC or VERITAS or the IACTs, where you would sort of more do like you have to decide where you want to point, but then you in exchange. Okay, recording progress. So then you get the angular resolution. Now coming back to the processes, of course, what we want to do is link the emission that we see to the particles themselves. And so a sort of rule that will come in handy throughout this presentation is that more or less, if we see gamma rays of a given energy, then we know that the particle that produced them is roughly 1 order of magnitude more energetic. So say you have 10 TeV photons, that would mean 100 TeV protons and slightly less energetic electrons. So more or less, you have to multiply by 10 in order to see, how energetic was the particle that made this photon. Something that is also relevant that will come in handy in this presentation is that these processes behave differently as a function of the particle energy. And so here I put a little sketch without any access of how the cooling time scale, so how fast the particles lose energy as a function of their energy. So as you can see, this is synchrotron, which I did not put here, but it's also a leptonic process where the electrons interact with the magnetic field. Depends very heavily on energy, so higher energetic particles lose energy faster, whereas, for example, PP is roughly constant, so it doesn't matter the particle energy. And this, again, will come in handy later. So I come back to the cosmic ray flux. And of course, in the past 100 years, since we know about cosmic rays and through gamma ray observations mainly, we've made quite a lot of progress in understanding like where these particles come from. And by now there's I would say, fairly established consensus that at least, in this like lower energy range of the spectrum, the cosmic rays are primarily responsible, so supernova remnants are primarily responsible for the cosmic rays. Now, you notice that I sort of stopped short of the knee of the sort of PeV, and the reason for that is that even though in principle, theoretically, it's possible that supernova remnants do accelerate particles past this energy, the observational evidence is lacking. And this essentially means that when we look at supernova remnants in the gamma rays, we don't see photons of the energies that you would need to then multiply by 10 and say, okay, PeV, 10 PeV, right? So besides, theoretically you can't, but in principle, the jury is still out there for whether observationally we confirm this. Now, on the other side of the spectrum, past this feature that we call it the ankle, which is the most energetic cosmic rays, you can make a really simple argument, which is essentially that in order to accelerate a particle, you need to confine it to the place that you want to accelerate it in. Because the more energetic particles will have very large Larmor radii. And in fact, these particles would have Larmor radii that are larger than the galaxy. So they would not be confined inside the galaxy. So we know that they must come from outside the galaxy. And when we look outside, we see things like AGN or gamma ray bursts or sort of this extragalactic sources. Now, of course, this sort of conspicuous middle range, which I've left, and this is what this talk is mainly going to focus. So like who's responsible for we call this, the cosmic rays past the knee, like around the knee and past the knee. So the sort of missing puzzle of like the remaining galactic cosmic rays that we cannot figure out where they come from, let's say. Now, before I talk about that, I want to focus again on this part of the spectrum, so the sources and start of the galaxy. Because when I say when we look outside, we see things like this. This is an AGN. This is actually a radio galaxy. It's Centaurus A, which is the nearest one, in fact. And so what you have here is essentially a galaxy that has at the center a supermassive black hole. And as a result of accretion into this black hole, there are these two really fast outflows of plasma that move relativistically, and these are called jets. Now, these things are really great to accelerate particles because they're large enough, fast enough, powerful enough. They sort of, they have everything you need. But of course, how exactly this acceleration happens is also subject to much debate. And there are a number of models. So I put here a little sketch, like, for example, magnetic reconnection, which would invoke like high magnetic fields close to the black hole, or shocks, which are discontinuities at some point in the jet, or shear acceleration, where you would have the discontinuity, sort of the shear layers of like the entire jet itself. And as I put in this little drawing, I put these little arrows, because depending on the mechanism of our acceleration, you would expect the acceleration to happen at a different place in the jet. So in principle, if we could see, where exactly the gamma ray emission is coming, we could also say something about how the particles are being accelerated. And you say, okay, then let's do that. Let's point, some ISET to Centaurus A and find that out. And of course, the problem is, always happens. The problem is that when we do that, we see something like that. And, it's quite hard to detect gamma rays in a planet with an atmosphere that's trying to protect you from the gamma rays. And as a consequence, even though I said the angular resolution of ISETs is good, it's still not great. And so actually this little green circle here is the PSF of Hess, so the points per function of Hess. And actually the very nice result here, the colors are the Hess emission from Centaurus A, is that you can see that this is not symmetric. So it's elongated with the jets. So we know that it's the jets causing the emission, but of course, it's very hard to say where in the jets and so on, right? So we cannot really do a detailed study of extragalactic sources. So now with this introduction, I'm going to introduce you to microquasars, which are sort of the perfect tool to answer both these questions that I've sort of posed. So with microquasars, we have actually a stellar mass black hole that is orbiting a companion star. So these systems are inside the galaxy. They're stellar mass systems, and they're, as a consequence, much closer to us. It's a similar thing as what I mentioned with the AGN. There is accretion from the companion star onto the black hole, and as a consequence, you have the launching of these jets. Now, of course, these things are way less powerful than AGN, right? Because the black hole mass is much, much smaller, but they're also much, much closer. So this sort of trade-off plays in our favor. Microquasars also, the timescales that govern the processes are also much faster than AGN. And so they have this sort of like short-lived phases of activity that also make it more accessible to study, in human lifetimes somehow. So the two questions that I sort of wanted to frame is both what can we learn about particle acceleration in jets in general using microquasars, and how much do microquasars contribute to this region with the question mark up to the knee. So to answer that question, first we have to see, okay, what do we know about microquasars? We don't know how many there are in the galaxy. In total, we know, around a few tens, like 20 to 40, depending a bit on what list you check. And of those, 4 to 6 are known to emit gamma rays. More on that later. And the reason that there's this sort of big discrepancy between the possible number of microquasars and the ones that we know for sure is that these things, as I mentioned, change a lot throughout their lifetime. So these two plots are a bit complicated. I don't want to go into detail. Essentially, what I want to show is that throughout different phases of their evolution or their lifetime, basically, they become much brighter or much harder in ratio. Sometimes they have outbursts in the X-ray, sometimes in the X-ray, sometimes they have it in the radio. And so there are big observational biases at play. So where do we look? When do we look? Really informs, which of the systems we detect. And maybe there is a microquasar that was very active 1,000 years ago and not anymore. And so we would never know about it, right? So there's this sort of aspect to it. From the gamma ray perspective, the first sort of indication of particle acceleration and past a certain energy in microquasars came from in 2009, where Agili reported photons above 100 MeV from Cygnus X3. And this was in a flare. So at a time where the microquasar sort of suddenly became very bright in the radio or in X-ray. And this is the one little point. Now, as I mentioned, there's this sort of, multiply by 10. So photons above 100 MeV means GeV particles, which is quite far from this region of need that we are interested in, but, you have to start somewhere. And then later, in 2016, similar thing, but now photons up to 20 GeV, so a bit higher in energy, were detected from Cygnus X1, which is a different microquasar from Fermilab. And in this case, the emission was correlated with the hard spectral index. So again, a different sort of point of the microquasar evolution. So as a consequence of this, the evidence was, okay, GeV emission is variable, and it correlates with these flares or spectral changes and so on. And so the observational strategy for the higher energies for TeV instruments was, okay, let's point at microquasars during these flares or these special times, these times where multi-wavelength information tells us something might be happening in the system. And so we did that for a very long time. The picture here of the telescope with eyes is Hess, but these are some screenshots of papers from MAGIC, Hess, also MAGIC, Hess, and Veritas all together. And the point here is that we did not detect significant emission from a microquasar during one of these events. Now, luckily for us, there's not only ISETs, there's also wide field telescopes like Hawk or LASSO that I mentioned earlier. Also Hess's side. And so in 2018, Hawk reported a really, really excellent result, which is that they detected very high energy photons from the jets of the microquasar SS43. And now we're talking about 10, 20 TeV photons, which means 100 TeV particles. So now we're getting closer to this, range of the need that I was talking about. Now, I will not go into details about this, the Hawk result, because the next seminar is by Sabrina, who will be talking about the sort of Hawk side of things. So I will not go into details about this. I just wanted to flash it because I actually worked in the Hess study of this source. So this is what I will tell you about. Now, what do we know about the microquasar SS43? So I actually put, this little cartoon that I showed you earlier. I put this little spiral jet, and that is because that's how the jets of SS43 actually look. This is a picture of a radio image of SS43 where you see that the precession of the jets is drawing this nice pattern. And one thing that we know about the system and that I sort of want to put in your brains is that the jets move at around 1/4 of the speed of light. That will be important later. So if instead of making this silly PowerPoint thing that I did, you ask someone that can use graphic design to make a nicer picture, it might look something like this. And so what you have here in this pretty artist impression is here in this bright spot, that's where the binary would be. And then you have the jets spiraling out, and this is sort of around 0.1 parsecs. We don't no longer see the jets anymore. So neither in optical or radio or X-ray, the jets sort of lose energy adiabatically and no longer emit radiation. And then if you zoom out and out and out, there's sort of at some point nothing. But then something really interesting happens, and is that suddenly, and on both sides, the jets suddenly become really bright in X-ray. And this happens at around 25 parsecs away from the black hole. Now remember, the spiral jets were around 0.1 parsecs on the black hole, and this is 25. So really different scales far from the black hole. And if you zoom out completely, you will see a picture like this. And now what we're looking at here is here in the tiny dot in the center is where the binary with the spiral jets would be. And then you have this sort of gap of nothingness. And then suddenly the jets become bright X-ray emitters. And what you see in red is actually something that's thought to be a supernova remnant related to the black hole in the system. And you see that there's this sort of spherical shape that's being deformed by the jets. And this is called W50, the name of this supernova remnant / whatever it is. So now this picture is very pretty, but of course I like this one much better because that's how the actual data looks. So what you're seeing here is the same thing, only with data, not with a pretty picture. And so in green, you see this W50 structure. This is radio emission. So you see the sort of the circular structure that is being deformed by the jets. And this tiny dot here, again, is where the binary with the jets are, the gap, and then the white stuff is X-ray contours that essentially tell us where the jet reappears and become bright X-ray emitters. And the whole thing is around 200 parsecs across. Now, if we put the Hawk emission on top, it will look something like this. So we have, two blobs essentially coming from the west and the east side. And for Hawk, these were point sources. So the point is that, okay, there is emission somewhere in the jet, but it's hard to pinpoint exactly where and how. And that's pretty much exactly, that leaves somehow some open questions because we don't know where and how are the particles accelerated. We also don't know whether they're electrons or protons. And we also don't know why the jets, after this 25 parsec gap, why do they reappear again? And that's pretty much exactly why where Hess comes in. And so I'm going to talk a bit about Hess results. Hess is an array of 5 Cherenkov telescopes in Namibia. We have 4 quote unquote small, so 12-meter telescopes, and 1 really big one, 28-meter telescope in the center. And our energy range is around 100 GeV to 100 TeV, and the angular resolution is 0.07. For people working in the X-ray band or radio band, this is horrendous, but for the gamma rays, until CTA is online, is as good as it gets, pretty much. And so we pointed Hess at it. And so this is the picture that I had showed you earlier. And now this is the Hawk picture. And now this is the Hess picture. And now here, this green circle shows you the Hess point spread function. And I know these two things, again, look like blobs. But if you compare them with the size of this green circle, this tells you that we can resolve it. We can do quite a lot more with it. And arguably, actually, the most interesting thing that we found when we analyzed this emission was when we split the emission into different energy bands. So if instead of looking at the entire Hess energy range together, we took the photons only from more than 10 TeV, then 2.5 to 10 TeV, and then even lower energies, we saw a picture like this, where the emission is coming from different parts of the jets, depending on the energy that it comes from. And this is the first time that we saw energy-dependent morphology in the TeV emission of a jet. Now, this already, I know again, this seems like 3 blobs sort of like moving slightly around, but this, we could extract a lot of information from it, because if you remember this cooling timescale sketch that I made before, the proton timescale, cooling timescale, is independent, roughly independent of energy, whereas the leptonic ones are not. And the fact that we see, these changing emission positions with energy is a very strong indication that the stuff, the radiation that we are seeing is actually made by electrons. Now, this is a very big caveat. The fact that we see emission from electrons doesn't mean that there are no protons in the jet. And in fact, we do know there are protons in the jet because there's iron lines in the X-ray emission of the jets. This just means that the protons are not making gamma ray emission as efficiently as the electrons are. And that's why we see the electrons first. They're sort of like loudest at being there. But emission being leptonic does not rule out hadronic acceleration. But the emission is leptonic. That's one thing that we can sort of say for sure. Now, if we go back to this image, but now we focus only in the highest energy band. So you see that here the emission is coming, sort of is focused on the place where the jets reappear in the X-ray, right? So like there is this like little gap here, and then the place where the emission is. And if you recall, again, this is the same tour as before. Now it has numbers in the axis. The time scale, the cooling time scale of leptonic processes means that the highest energy particles will cool the fastest. And that means they will not get very far from the place they were accelerated in. So in a sense, the highest energy particles are, sort of pointing us to where they were accelerated. And the fact that we only see above 10 TeV photons from these 2 locations tells us that that is where the particles are being accelerated. So we now can tell that particles are accelerated in the place where the jets reappear in the X-ray. And now this sort of picture is forming, right, where you have like something here, accelerating particles, then the particles are taken and then moved with the jet. And so, of course, now, if we knew how fast particle cools, and we knew how, if we knew how fast the jet moves, we could describe this movement, right? Because you have particles being injected and then move with the jet. And so we don't know the jet velocity at that stage, but we do know how particles cool. So we can put both 2 together. We need to find out how fast the electrons lose their energy, and then we will be able to measure the speed of the jet when it reappears here in the X-ray. And so this is sort of a sketch of the idea. This black stuff is the X-ray contours from before, a bit simplified. This is the position where the particle acceleration happens. And so basically what happens is that somewhere here you have, something accelerating particles, which means you inject an electron spectrum. And then these particles are moved with the jet. And by the time they make it a little bit further, they have cooled. So the highest energy particles are no longer there because they lost their energy, right? And so in this picture, there's 3 things we don't know. We don't know what the distribution of electrons was to begin with. We don't know how it cools, and we also don't know the velocity of the jet, right? But the nice thing is that we can find this out by doing SED modeling. So we have the measured gamma ray spectrum by Hess, and we put it together with the X-ray flags and also upper limits from the radio and the GeV. So here this west-east refers to both sides of the jet. This is kind of irrelevant because they're both very similar, so I'm going to focus on the west here. And we know that the emission, remember, is leptonic. So it's inverse Compton and synchrotron. So we model, we put some lines through the points, and we know now that the magnetic field is around 20 microgauss, which is consistent with previous estimates from the X-ray. And we also have recovered the injected electron spectrum. So we know that it needs around 0.1% of the jet kinetic power. And also, interestingly, we know that the shape is e⁻², and that energies have to reach at least 200 TeV or higher. And as a consequence of this fitting, we also now have the plot that I showed you earlier, which is the cooling time. So if we go back to our little sketch, we actually know now this. So the only thing that we have, the only question we still have is how fast is the jet moving? Because remember, we have particles injected, they moved as they cool. Now we know how they cool. So all we have to find out is how they move, essentially. And so we do that by, first we take the gamma ray data and we split it into different little boxes. And each of these little boxes, we derive the flags. And then we simulate this process that I described with injection and transport with a Monte Carlo code, and we fit for the velocity. And when we do that, we recover a velocity of around 8% of the speed of light with some systematic and statistical errors. Now recall, as I said at the beginning, that the jets launch with around 1/4 of the speed of light. And as I said a minute ago, that the maximum energies have to be 200 TeV or higher. Now, in order to reach those energies, the jet cannot have deaccelerated very much, meaning that the jet must have been coming relatively fast, and then suddenly it's no longer so fast. Suddenly it's 8% of the speed of light. And if you look at these two numbers, especially taking into account the errors, they're around a factor of 4. And this reminds us of something, it's a shock, because shocks are really good at accelerating particles, and they're exactly that, a discontinuity in the medium, so you would have something faster and then something slower. And in fact, if we then looked at the X-ray picture, and I will not go into any detail of this, of course, because there's a talk by Samar in this series of seminars, you can actually see that at that location, there's a quite sharp discontinuity. So this sort of adds to the picture that what's happening there is that there is a shock at that location. So we now sort of have this clear picture. We know that the jets reappear because there is a shock, and we know that particles are accelerated there by a shock. And so to my initial question, so that's sort of the picture that remains. This is the system again. And we know that here, in these two locations, there are shocks that can efficiently accelerate particles. Now, to the questions that I asked at the beginning, what can we learn about particle acceleration in jets using microquasars? The answer is obviously something, because with SS43, so with this study, we could for the first time identify the particle acceleration mechanism taking place inside of a jet. And if you want to then extrapolate to, for example, AGN, there's many properties of jets that scale nicely with the black hole, so it's not completely crazy to do it. But in my opinion, what is a bit crazy to do is extrapolate based on one system, right? Because SS43 could be a total outlier, could be like the really most special system in the galaxy, and there's nothing like it, and nothing else behaves like it, right? So it's very hard to make a really definite statement when you have just one single data point, right? And in terms of the contribution to the galactic cosmic ray up to the knee, with SS43, the answer is, in principle, you can, at least with what we knew with the Hess data. So here, this is the Hillas condition, this thing I mentioned earlier of, if you want to accelerate particles, you need to confine them with numbers that belong to SS43. And the answer is that in principle, you could reach 10 PeV particle energy. But of course, again, it's very hard to make a statement if you only know one system, right? Because one system would not contribute a lot to the cosmic ray flux. So we were sort of at this
I just
impasse.
want to point out that this jet is non-relativistic, so it's a bit, you have to be cautious when you compare it to relativistic jets in AGNs.
Right. Right. Yeah. But I mean, this is the speed that we're using here. And okay, yeah, I mean, the jet is quarter of the speed of light. But it was hard to make a statement with only one, but luckily for us, Hawk is seeing everything all at once. And in 2022, they announced TeV emission around a second microquasar, V4641 Sagittarius. And now, again, in the next seminar, Sabrina will talk about the Hawk results. I will not go into details about the Hawk result. I just wanted to flash here the images, because they're very nice. So this is the significance map above 1 TeV, really above 10 TeV, because you see that the spectrum only starts there. This is where the microquasar is, and there's this large emission region, which extends also to more than 100 TeV. So who's this guy? Who's V4641 Sagittarius? Now, this is a bit of a different system. SS43 is a high-mass X-ray binary, so the companion is massive. V4641 Sagittarius, not so much. The companion is like 3 solar masses, so people call it a low-mass X-ray binary or intermediate mass X-ray binary, depends a bit on what you prefer. And the reason that this system became known to us mainly because in 1999 it underwent a gigantic flare in X-ray. It was brighter than the Crab by a lot for a little bit. And also at the same time, radio observations indicated the presence of superluminal motion. So essentially, you have this compact blob that's moving so fast that seems superluminal. And this is not really superluminal motion. What this indicates is that there is relativistic motions at a low inclination angle, so a jet pointing at us, basically. And these are these sort of radio blob images. Now, this, the fact that the jet is pointing towards us has actually been used by some people to sort of speculate, there's other indications that the system might be like SS43 in other aspects. So maybe we're looking at something like SS43, but from a different angle. So sort of, looking into the jet as opposed to looking at the jet like that, like we do with SS43. So we pointed Hess at it, and I'm going to show you some preliminary plots because the Hess paper is not published yet about the detection. So we also detected it with Hess. And we see a very similar picture as that with Hawk, only a little bit sharper because the angular resolution is a bit better. And so here you have the position of the microquasar, and then you have this really long and narrow, so this sort of like, like a 1 degree long to like 0.3, 0.2 degrees wide emission. And if you take the usually accepted distance of 6.2 kiloparsecs, this thing will be 100 parsecs times 15 parsecs long. So really quite long. Something interesting is that V4.641 is not at the center of this emission. So it's actually a little bit, there's like 1/3 of the emission on top and like 2/3 below. And the reason that we know that it is V4.641 is because in galactic coordinates, this thing is 5 degrees below the plane. So it's not in a crowded region. There are no other counterparts that will, possibly explain this emission other than V4.641 Sagittarius. So with HESS, we could also measure the spectrum, and we actually fit a model, and we find that a single elliptical component, so just one model component to explain the entire emission, works best. And the index that we find, so you can see this here in the plot, is quite steep. So the flux is still increasing at higher energies. We also tried two-component model, and we find that that's not preferred because basically the emission is consistent with itself throughout. So there's no spectral differences at any point sort of throughout this big region, and we find no evidence of distinct emission regions. So we cannot split the region, like if we look at the map again, we cannot really split the region into like different ones. It just seems to be statistically preferred just one long component. Now we can put on top the Hawk flux, and nicely they match nicely. I cut, of course, the plot here at 100 TeV. The Hawk flux extends past 100 TeV, but what I was interested here is in the region where we can compare with HESS. And this, of course, begs the question: what in the world is this thing? Because remember, I mentioned that the jet is thought to be pointing at us, and this is based on these radio observations. And I put the radio blob picture just because you can see here on the y-axis, this is arc seconds. And this here is degrees, right? So if you actually put both things to scale, you would basically not be able to see the radio emission. And instead, we have this really extended, elongated emission in the gamma rays that was somehow unexpected. This is not what you would expect to see from a jet that's, like a blazar, like micro blazar, right? Like you would not expect to see elongated emission. You would maybe expect a point source or similar, right? So this is sort of passing. Of course, one would then say, okay, can we get any help from other wavelengths, right? Like what do, X-ray radio tell us? And the problem is that not much, because we have a sort of combined problem in that this system is a bit far off the galaxy, so 5 degrees below the plane. So many surveys and so on just haven't covered it. And a lot of dedicated observations focus on a narrow field around the binary because there was no indication that there was anything else happening in the large scale. So there's, there's an X-ray detection and so on, but they all focus on the binary itself. Luckily for us, there were some Chandra pointings that were sort of like covering some of this area, although not all of it. And now Mitsuji derives some Chandra upper limits. And so if I put it all together, I get an SED like this. So here you have Fermi lat upper limits that were derived by Marianne Lemoine-Humat. And then the Hess points, the Hawk points, and then the Chandra upper limit. And now we can play this game of, okay, let's try to pass a line through these points. Note that here I'm not even fitting. So this is just literally me passing a line through points. And if I adopt a leptonic scenario, right? So you take some of these, interstellar medium radiation models, and I have to take a relatively short injection time to match well the shape of the gamma ray peak. We find that the magnetic field has to be relatively low to justify the node detection in the X-ray. So it has to be less than 5 microgauss or so, depending. You can play a bit with the parameters. And remember, with SS43, it was 20 microgauss, so it's significantly smaller than the other example that we have. And something else that's quite notable is that you need a lot of power to explain the flux. So this source is really bright. And this little power that I write here is the amount of power going into electrons. And now, if you think about the power that's emitted in the X-ray of the source right now, it's more than that. So we have this sort of problem that this source seems to be way brighter in gamma rays than in any other sort of observable that we have of it continuously. Of course, in 1999 it was very, very bright, but that lasted a few days, right? Not 2,000 years. And if you then take a hadronic scenario, you have a similar situation, but here the question is how much dense matter is there around you, because you need either a lot of protons or a lot of matter, right? Like one of the two needs to be true. Something that you need as well is a relatively hard spectrum in order to match, to not get into trouble with Fermi non-detection. And so this is the amount of energy you need, which of course depends on how much dense matter is around the system. Now, this was sort of all up to date up until 2 weeks from now ago or so. Last week, there was this huge discovery or more than discovery, like reporting of a discovery, which was that LASSO detected photons up to 800 TeV from the system. And I remember, if you do this, multiply by 10, whatever, this brings you way past the need comfortably. So 8 PeV, if you take it just a factor of 10. And this is really, really exciting and also really surprising somehow, because there is nothing indicating that this source is going to be the most energetic particle accelerator in the galaxy. So I put here a collection of the maps that we have so far. So this is the HESS map with the PSF. These are the 2 HAWC maps that I showed you before. And now this is the new one from LASSO above 25 TeV. Again, I'm not going to go into a lot of details about the LASSO result, but I will talk about this a bit later. And I wanted to add the LASSO points to my plot. And, I found that very nicely. They connect quite well. And if we now play the exact same game and, put some lines to some points, we find that in either scenario, so whether you have a leptonic or hadronic scenario, you need a particle cutoff at a few PeV at least to match the flux. So this source is definitely a pevatron, or even a, I don't know what you want to call if it's more than 1 PeV, super pevatron or whatever. So this source is accelerating particles to the PeV, to the energies that we need for the need. Now, of course, this one-sum modeling that I'm doing here, where I put all of the emission into one SED plot, is not the whole story, because something else you have to then explain is how do the particles travel to this 100 parsecs distance without cooling, which would be, for example, a problem, I would say, for the leptonic scenario, which is not reflected in this plot. So coming back to the question of what can this source be, in my mind, there's sort of these 2 possible options. One of them is that, in a sense, it's quite obvious, right? Like, we see something elongated and it has this structure. What we see is the jets themselves. And now the question is, of course, why does it look so different from the radio jet, where we think is pointing at us? Maybe there's 2 jets in the system. Why are they so different? So that's somehow like one of the possibilities. I find that right now, with the data that we have, it's a bit hard to constrain that scenario. Another scenario that's also a possibility is that the jet is indeed pointing at us, but it's accelerating particles that escape and then interact with something. And that something is what has that shape, right? And so in this scenario, for example, you could have, for example, a molecular cloud that has, this elongated shape, and then escape protons are diffusing in any direction. And then because of the presence of this gas, we see emission in that shape. Now, in order to test this idea, we would need to know, is there really gas at that location? Now, this idea has sort of some cons. One of them is that, as I mentioned, this thing is 5 degrees off of the galactic plane. This is several hundred parsecs, whereas the scale height of molecular gas in the galaxy is much smaller. And also, if you look at the Planck dust maps, which should trace the presence of gas more or less, you don't see anything striking. But of course, there could be something that we've missed. And for that reason, there will be dedicated observations. They're now misleading with the Noboyama telescope in Japan, where we can answer the question, is there gas there or not? Another option is, instead of gas, maybe you have something like a magnetic field structure. So you have, for example, an ordered magnetic field, which is not a crazy thing to have because it's, as I mentioned, a bit far off the plane. So you don't have the mess of stuff happening in the plane. So it's easier to have something ordered. And then escaped electrons or protons are trapped in this filament. And then they interact with, for example, diffuse target photons. And that's why you have that shape. Now, in this scenario, you would also expect X-ray emission tracing those electrons. And that's why there was an XMM proposal led by Xiaojie Wang, who is the first author of the HAWC paper on this source, which hopefully will tell us if there's something in the X-ray or not. So again, sort of to summarize a bit, I showed you that in the GeV, we had evidence of 2 microquasars emitting GeV particles, both in this transient way, so like during a flare or a state change. Whereas in the TeV, the emission seems to be persistent and actually more in large scales. So actually, we had the question of is this picture holds? Is the GeV emission always transient? So together with Guillem Martí de Besa this summer, we looked at the entire Fermilab data around another microquasar, GRS 1915, and we found actually a persistent new source that is coincident with the microquasar. And if you take into account, what other possible counterparts there are, we find that the best one is the microquasar itself. So the paper is on arXiv. You can click on it if you're curious. So we thought that was nice because you can go to this plot and now this no longer holds. So GeV emission does not necessarily have to be transient. And even more excitingly, again, last week, LASSO reported 25 TeV photons coming from that exact source. So now we have, again, evidence in the GeV, and also in the TeV. But it was not only that source. There was really a revolution happening last week because LASSO reported more than 25 TeV photons from 5 different sources. And there will be a dedicated seminar on this topic, so I will not go into any detail because it's not my place. But I wanted to sort of show you some of these results and rather talk about how they compare or how they complement the stuff that I already showed you about the systems that you already, quote unquote, know because I told you about them. So LASSO detects 2, quote unquote, known sources, so SS43 and D4641. We knew there was TeV emission from them, but also 3 sources that we had no idea there was TeV emission coming from them. One is this GRS1915 that I mentioned that we detected also in Fermi, Cygnus X1, which is one of these 2 GeV sources that was transient in the GeV as well, and also Maxi 1820. Something interesting is that LASSO sees all persistent emission. And when the statistics are high enough, so these are these 2 cases, you can see here the significance, is 10, 12. These sources are extended. And these sources, which are, the like 5, 4 point something sigma level, these are point-like. Again, not going to go into a lot of detail. Another exciting thing is, however, the energy at which they reach. I already mentioned B4641, which reaches 800 TeV, but all of them except Cygnus X1, because it's low statistics, reach well above 100 TeV. But still, B4641 stands out as not only the most energetic, but also if you look at the y-axis in this plot, also the brightest. So it's the brightest one by far, especially at this very high energy. So this really begs the question, what's so special about this system? So I told you that I was going to comment a bit on the results and how they relate with what I just told you. I wanted to show you this plot because I made it 2 days ago and I thought it was interesting, of this GRS1915, which is this source that I mentioned we detected with Fermi. And so I wanted to put together in the same plot the Fermi spectrum and the LASSO spectrum and see if, they can connect or if they're clearly incompatible. So what I put here is the blue points are the Fermi SED, the purple points are the LASSO SED. I also put here the sensitivity curve of Hawk, because I actually think that it's also quite intriguing why Hawk has not reported on this source, because in principle they should also be able to see it. More on that, and you could in principle pass a line that goes through these points, right? But of course you could also put an elephant inside of that line. So the conclusion that I got from this plot was that these 2 components could be the same, but it's very hard to tell with such a big gap in the middle. And that is the job for instruments like HESS, Magic Veritas, to follow this up and to sort of cover this range and to see if there is also emission in this range. The other source that I wanted to mention was SS43. Again, not going to go into details because there's a dedicated seminar. The most exciting thing, I think, about this LASSO result is that they find a new component above 100 TeV. So these pictures are kind of similar to what I showed you at different energies, but now they're in the inverse order. So this is lower energy, middle energy, and very high energy. And so you see here that above 100 TeV, they see emission that's sort of coincident with this white stuff. And these white contours are actually neutral gas. And there was already reported some Fermi source that seemed to be pulsating that was coincident with that place. So there you would have the gas, and this is interpreted as a hadronic component. So I mentioned earlier, just because we saw the electrons at lower energies doesn't mean there are no protons. And maybe this observation by LASSO can help us constrain how many protons are being accelerated in the jets of SS43, which is really great. In terms of consistency with the previous studies, below 100 TeV, the picture seems pretty much the same. In terms also, of course, the angular resolution is not so good, but in terms of the position, although I was a bit intrigued because there was this plot in the paper where, so this is the sum of the LASSO points. So here they have, west, east, so like the 2 lobes, and then this extra component, and here they sum them. In gray, these are the HESS points, but they are not summed. So it's like east and west. And I was curious, how do they compare when you compare apples to apples? So really sum them. And what I found is they actually don't match. So there seems to be more flux in the LASSO results below 10 TeV, sorry, which I also thought it was intriguing. But also, to be fair, this is like a factor 2-3, and the HESS points include systematics, but I think the LASSO points don't. So maybe this is the kind of thing that once you include systematics, completely goes away. But if not, it's also quite interesting. So now I'm coming to the end. I wanted to come back to the questions that I asked, what can we learn about particle acceleration in jets using microquasars? And the answer is clearly a lot. But of course, if you recall, the reason that we could do what we could do it, understand the particle acceleration with SS43, was because of the angular resolution, right? And the only source that has been detected by an ISCT besides SS43 is B4641. And now we have these new ones from LASSO, but you've seen the LASSO images. The LASSO and HAWK are really great at telling us something is there, but they're not so great because there's limitations observationally to really tell us the details, like where exactly is the emission coming and so on. And for that, you need pointed telescopes like ISCTs. Both the current generation has Veritas and MAGIC, and also the future. So we have CTA coming online in the next few years, and this will be a huge jump in sensitivity, but not only in sensitivity, also in angular resolution. And I put here a plot from a paper by Georg Schweffer, who developed a method called FreePack to reconstruct CTA data, which brings the angular resolution of CTA down to the 0.01 degrees. And again, if you're in the radio or X-ray bands, you're not too impressed, but for gamma rays, this will be a real revolution in what we'll be able to do. And also something really important is that we need the information coming from both the radio and the X-ray bands to tell about, the structure of the systems, the presence of shocks, the magnetic field. So we need to go in, it's not enough to just say there is TV emission. We need to really do a detailed study if we really want to say something about jets as particle accelerators. To the second question of the contribution of the galactic cosmic rays up to the knee, before last week's, I used to say, yeah, in principle, yes, but it's a bit hard to tell. I think that after the LASSO results, it's fair to say, yes, there is a contribution from microquasars up to the knee. And now the question is, how big is this contribution, right? And of course, the answer of this depends on how common something like B4641 or SS43 is in the galaxy, right? And so now we are finally at the position, thanks to LASSO, that we can now start thinking in terms of the population itself, right? So there are, 30 or more X-ray binaries from which jets have been reported in the galaxy. What makes the 5 that LASSO sees special, right? And if you look at their sort of, more general properties like the jet speed, the compact object mass, the black hole mass, nothing really stands out because, as was pointed out, SS43, the jet is semi-relativistic, but B4641 is very relativistic. Or some are high mass X-ray binaries, some are low mass X-ray binaries. There doesn't seem to be sort of a very clear trend. To me, something that's an intriguing hint is that in most cases, whenever there's statistics, the emission seems to be extended, which indicates that it's probably not coming sort of from like very, very close scales to the black hole, but rather maybe coming from interactions of the jets themselves with the environments. But of course, we will see about that. And I think the conclusion is that it's a very exciting time because we have a lot of work to do to understand, why are these systems special? How many of these special systems can we expect? And if we answer these questions, we will be able to tell how much do they contribute to the cosmic ray flux. And so I just wanted to finish with showing again the first picture. I put that question mark, and I think that, I hope that I've convinced you that at least B4641 Sagittarius definitely contributes, or a system like B4641 Sagittarius definitely contributes to the cosmic ray up to the knee to some extent. Thank you.
Thank you, Laura. That's a really nice summary. Thanks for the excellent talk. So let's open the floor for questions. Please raise your hand. And Susume, go ahead.
Yeah, hi, Laura. Really exciting results. So many all at once. I have corresponding to many questions, but I don't want to take up the whole floor, so I'll just ask one for now and ask the rest later, maybe after others. So about GRS 1915, the Fermi results, the extended emission, that it seems to be different from the direction of the jets, right? And so I think, yeah, so the blue line is the direction of the jets. And if I understand correctly, there are infrared and radio sources that has been suspected as like hotspots, and the radio morphology look a bit like radio lobes. So how does it compare with respect to like the gas distribution H1 or molecular?
Yes.
Is it,
so I don't have that plot here, but if you click on the if I think I listed it as the like literature in the paper, it's there. So the Fermi source is a point source for Fermi, right? And a point source for Fermi is actually like 30 parsecs big if you project it to the size of GRS 1915. So it's very hard to say exactly where. The scenario that we prefer is probably hadrons escaping GRS and interacting. There is some nearby gas somewhere here. It's also in the paper. And the regions that you mentioned actually are somewhere here and there. And we don't find any significant emission from them in the Fermi analysis. So we don't find any emission from the infrared regions.
Yeah. Okay. Yeah. Yeah. Thank you. Well, I'll end for now, and if there are others, or unless if there are, okay.
Go ahead and ask your question, Susumo, the second question, and then maybe after that we take again.
But quickly,
Okay.
so quickly.
Sorry?
I think will be many questions. Just try to be a bit more.
Yeah. Okay. One more. So about V4641. So you mentioned the radio evidence that the jet might be pointing toward us. If I understand correctly, if I look into the paper, it's not really as secure as like for the case of GRS 1915, where you clearly see two blobs, and you have good constraints on the velocity and the angle. So it's just, I think it was a variable extended source, and that faded away, and from that they inferred the velocity and the angle. So maybe that the inference that the jet is pointing toward us is not the most secure, right? Yeah. But has there been this outburst that happened in 2000? It's the only one that has happened.
So that's why I didn't sort of go into this. There's this option that what we see is the jets, and they simply are not pointing towards us, right? And I didn't discuss it so much because I find that I don't really have any good. I think we would need to have some evidence of the jets in the radio, maybe. But as far as I know, correct me if I'm wrong, at least in sort of published papers and so on, there hasn't been any other reports of the jet besides the one in 1999. So that, of course, and as you mentioned, this is not the best. Other systems have a much clearer presence of a jet. So this is an asterisk to it for sure.
Yeah. Okay. Thank you. Thank you very much.
Please go ahead, Evgeny.
Thank you for the talk. I think it's really convincing case for the leptonic emission. Just wanted to ask to make sure, when you model your SCD, the inverse Compton component is coming from scattering of extragalactic microwave background. Is it correct?
Yes. So not only the microwave background, also we have this Popescu et al. Model that has also like the infrared and UV bumps of the emission in the galaxy. And so this is a sort of entire galactic model, and we chose the position of SS43, and that's the model that we get. And we played a bit with it to make sure that didn't matter.
Infrared, how far into infrared you are?
I don't know the answer by heart, but it's in the paper. If you go to the paper in the supplementary material, there is the plot of the SCD of the target photons.
Okay. Then I have actually one comment regarding the contribution to the galactic cosmic ray accelerators. If I remember correctly, the overall power of the galactic accelerators should be something like 10 to 43 erg per second.
Not at the knee, right?
At the knee, even less. Even less.
No, Evgeny, it's 10 to 41 maximum for all cosmic rays, and about 10 to 39 erg per second around the knee.
Oh, so you want to produce cosmic rays at the knee, but not below the knee.
Right. I mean, below the knee, there's supernova remnants can take care of it, right? You don't need to explain all of the flux with microquasars. The idea would be the microquasars come in. It's a second component that comes in at higher energies.
The problem is that we don't see any second component up to the knee. It looks like a single component.
How you know, Evgeny?
I don't know. It looks like. I don't know.
No, it looks like there are very recent results just indicate even that could happen. You could have several components. But regarding your first question, so again, is not 10 to 33 arc per second, is less than 10 to 41 arc per second, the entire component of galactic cosmic rays. And around the knee, you need only 10 to 39 arc per second. If you have a source for PV protons, 10 to 39 arc per second, that in principle is sufficient to provide entire flux.
Principle, yes. Then you have to match the components. Yes.
Yeah, but that is always business as usual. And that is over the times when we are saying we have a unique cosmic ray spectrum. Could be there even 2 or 3 components.
Who knows? Who knows? It could be many. Yes. Okay,
No,
thank
no,
you.
that you are asking a question. Yes, who knows? That would I should say who knows, but in fact it cannot exclude that.
Okay.
More questions? Okay, if there are no questions, maybe you could start some discussion. Actually, we already started. And about the general, you could express your view on these results.
Should I stop sharing?
Sorry, I actually had one more question.
Yes,
Could I just
Susumo,
ask
go ahead.
and before? Yeah. So again, for P4641, so in the hadronic interpretation, even when you assumed 100 or 10 per cubic centimeter for the gas, the energy requirement for the proton power is pretty high, wasn't it? 10 to the 38?
Well,
Thanks
no.
per
Okay, so
second.
this is, I'm assuming it's short time, right? You can also assume much. I mean, this source, the age of it is somewhat known because of it's far away from the galaxy, so it was kicked out, and so there was actually it's a really nice paper that like traces back, like when did it get there. And we know that this is a bit lying. That's why I showed energy and not power for protons, because of course if you put if you put 1 million years, 500,000 years, we need a lot less. Then the problem becomes confinement, right? So I think for protons the energy is not power. The problem is not power. You need either high density or some way to confine them there for a long time.
Yeah. Okay. Maybe smaller than average diffusion coefficient.
Yeah. Exactly. Yeah. But the proton for protons, the power is not a problem because you can put much longer times. The problem for the leptonic model is that if you put much longer times, then you get into trouble with the GeV non-detection.
Yeah. Okay. Thanks.
Laura, I have a question.
Yes.
Even our discussion. So we have this giant bright gamma ray source 1908 just above 43. So of course it's quite close, and we have to have very good PSF. Even PSF could be better than this distance, but nevertheless there are tails of PSF. So
yes,
in that case, Hawke and Lasso are in a worse position than Hess.
Yes. Yes.
So I understand. I mean, at least personally, always I was so pessimistic, thinking we should really distinguish. So Hess did that. Now, question is, you are also in Hawke.
Yeah.
Do you think Hawke could solve fully this problem of having a significant contribution from 1908? Maybe this question should be Sabrina, but nevertheless, since you are also in the same group, when do you compare with Hess and Hawke? Could you tell us how you could see the superiority of Hess compared to not Hawke, just this kind of instruments, even Lasso?
Yeah. So some context also for other people. 1908 is this bright source that's near SS43. So this is the actual Hess map, and then we subtracted it. And also in Hawke, I also have that plot. It's as Felix said, even more of a problem because this source is actually kind of on top of the jets and you need to subtract it. And I mean, I think you're right, Felix, that the bigger the PSF, the worse this problem becomes. And also because 1908 is sort of like, it's very bright and you don't expect it to be Gaussian, right? Like even the models that we model 1908 with are limited in that they're very simple. And so in the Hess, I mean, I can talk more in detail about the Hess analysis because I in the Hawk analysis, I was not involved like directly in making it. In Hess, we estimated very carefully, like, what happens if you don't model 1908 or if you model it very poorly. And actually the systematics, this affects mostly this Western lobe, so this side here. And in the Hess result, the systematic band of the Western lobe was bigger than the East, and that's because of that effect. And so I would assume that the case in Hawk is very similar, that you simply have, really big flux systematics, especially for the Western case. And I mean, I actually mentioned, the comparing Hess with Lasso below 10 TeV, there's this small discrepancy, right? And actually, my guess is that this discrepancy comes from that, because if I read the paper correctly, Lasso models 1908 with a power law, and I lost the slide, but you can see that 1908 is not a power law. It's a log parabola. So you really need to get 1908 right before you can say something authoritatively about SS43. And even when you get it right, the systematics that it introduces are high. So I think you're right. It's better with Hess, but I think it's possible with Lasso and Hawk. Maybe the Eastern one is sort of like the good reference, to compare somehow to both. But I think it's a problem. It definitely.
Yeah, in that case, you mentioned CTA, which is really very, very important to resolve with even better angular resolution.
Absolutely.
But just notice maybe even earlier could be resolved with locked this Cherenkov telescope array on the site of, and that will be at highest energies. That is important. And so I think it's really, I just want to say, my question was that Cherenkov telescopes could be extremely important even for future for these sources. Even we are very impressed by results Hawk and especially Lasso, but still I think to comprehensive understanding of this source, this specific SS443, because of this big giant round. So Cherenkov telescope could give a lot of new information. And especially when it highest energies, that was emphasized, LACT will operate exactly in that energy band around 10 to 100 TeV.
Yeah. Yeah, I mean, like this is what I said here, right? Like, I think this actually shows very nice the complementarity somehow, right? Because you have Lasso and Hawk telling you where to point the telescope with the high angular resolution, right? Because it would be impossible for something like Hess. I mean, CTA will do a survey, but still to find these things, right? Because I mean, SS43, we needed like hundreds of hours, right, to detect it. So this is not something you can do with Hess for every source, but it's nice to now do the follow-up of sources we know are there. So I think both are really important in that way. Yeah.
So even we see very impressive SWGO, at least theoretical sensitivity curve. Still, I think CTA or Cherenkov telescope like CTA would be crucial.
But you need both, right, Felix? Because I mean, something that I find quite funny is that V4641 is the perfect Hess source, right? It transits overhead from Hess, like it's at the perfect declination. It's super bright, and yet we didn't see it because we didn't know that we had to look at it, right? So we had to be told by two like northern instruments that there was this bright source which is passing right above our heads, and that's because of the limitations of Cherenkov telescope, right? So you also need something in the south that sort of tells you where CTA south should point. Otherwise, you might miss something like this, right? So I think both are.
This for sure. This for sure. Only one thing we should be. I mean, now people seeing these results by Lasso. If you are talking about highest energies, it can be done everything by Lasso, but in fact, a lot of new things could come with Cherenkov telescopes. So, by the way, just for your information, this LACT even is not the best position for observations. They are often cloudy, but for this specific source, LUC could observe 200 hours per year. So that could be. Some questions, more questions?
I think Paolo raised his hand.
Yeah, I just want to follow up with Felix, the angular resolution, but focusing on the extended emission. It's like 2 years ago when there were similar talks, Lasso and Hess disagreed. And so how well does Hess handle extended emission now? And you plot everything on the same graph, but is that allowed given the different angular resolution? What's the latest?
So I think this is, ISCTs have done like a huge improvement in terms of extended sources in the past few years, namely because now we do this like 3D background technique and 3D analysis technique, where basically we derive less information about the background from the field of view. And we also can model stuff, you know, we don't do this like on-off where you like cut out a little circle, you actually like look at the entire region. So we, you know, something like V4641 is in a sense like not a problem for Hess at all. When you get to even bigger, right, like Geminga signal scales, that is all like, you know, like something out of the order of the field of view of the telescope. That's when you really need, you know, special techniques, and even then the systematics start killing you. But at least for the extensions that we're seeing now, like I think I have somewhere the lasso plots. I have too many slides. But at least for, you know, for the extensions of the lasso plots, you know, which are like 0.5 degree point and so on, like that, that's fine for, at least for Hess.
Okay, cool.
Yeah.
And then does the agreement for V4641 apparently mean that you've seen everything for both?
Yes. Yeah, I was very happy that plot made me happy, because of course, you know, we are also limited by the, you know, something that sometimes people don't know is that in ISCTs you usually have to cover a region where you think your source will be, so that you take the background from the other region, right? So previous analysis of this source, actually the stuff that we published before, you know, only expected signal from here. And so they took all of this region for background, which, you know, is not correct. But how would we know that we had to do something different, right? It was only when Hogg showed the emission that we knew like what to cover, and then we could see the emission, right? So that is still a problem. Like something extended that we don't know is extended will always be a problem for an ISCT. But if we know the extension and it is not like much bigger than our field of view, then you can do with.
Thanks.
Yeah, just to add, Paolo, for a question about Hess and then Lasso, also Veritas Lasso, you are right, always there are some discrepancies because different techniques, but at the end, in most cases, these discrepancies have been solved. So, yeah. I mean, so if you know results already, then you work on Cherenkov telescope data analysis and typically find out the reason of discrepancy.
Yeah. And I want to add that like very often these discrepancies come, I mean, of course there are exceptions, but very often they come from comparing a Lasso or a Hogg result with an ISCT result of like 5 or 6 or 10 years ago, where the technique was different, right? Where people were typically not doing this 3D analysis and so on. Now that people do the new results, the agreement is usually much better. So there's that to take into account. Like if Lasso disagrees with a Hess paper from 2009 or something, I would not be surprised, right? Because it might be that there was some kind of different background estimation that did not take into account extended sources.
This is really a very important point, but nevertheless, Laura, I mean, if you know the result, then you work a bit more focused on the problem. I mean, if you don't know the discrepancy, so you are right now. We are advanced technique, but I think also because as we know discrepancy, we won't solve, and then that is a issue.
Yes.
Some other questions. Actually, we are approaching. We still have time, but maybe I could just tell you that we will have already, you know, 2 more talks on Hogg and Lasso. All these are really resulting very exciting. Hogg just published paper in Hess for this source 4641. Lasso submitted, and there are some more other results. And I think it's good that Laura introduced a bit also Hogg and Lasso. So results we will discuss them in next two seminars, and plus we'll have a multi-wavelength by Samar. But I guess we'd like to have discussed this physics after this 4 talks. And for example, I'm sure we'd like to hear some opinions, for example, from Andrei Bykov, where we developed some acceleration model and thinking this could be a bit different way than we think in a traditional jet interactions. So maybe you could think we already started to fix our program for next January, because maybe I should discuss that with Reshmi Paolo before, but nevertheless, we could think to have one, not a seminar, just very long 2-hour discussion when everyone could talk about these sources. These really are very highlight sources. And so it will be good after these observational results plus multi-wavelength, we maybe could meet somehow next year, maybe some addition, some in addition to our talks, to have some special seminar will be not a talk, but just discussion. I'm sure there are a lot of interested people in these sources. So, okay. So Reshmi, I see there are no other questions, right? So maybe you could close.
Yes, I think we can close. And thank you all for coming. And let me just remind people that we will meet again in 2 weeks. And I think this week was a special time because of the change of time in Europe. But I think from next week, everything will be back to the usual time. So thank you everyone. And if you didn't get the email, send me your email so that we can add you to our list. Thank you very much, Laura. That was absolutely excellent. Okay, bye-bye.
Bye.
Yeah. Bye. Thank you. Bye.
Bye. Thank you very much.